Having talked about between subjects and within subjects factorial ANOVAs, we're now going to talk about the mixed model ANOVA, which has at least one independent variable which is within subjects and at least one independent variable that is between subjects. And there's multiple reasons we would be using this technique. The first reason is basically that's simply our design, but I do want to talk about a couple of situations where we'd be using it more as a methodological fix than necessarily a design or theoretical series of hypotheses. So what is a mixed design? A factorial design with at least one between subjects independent variable and at least one within subjects independent variable. It is a partial cross design at that point. Now again, as a reminder, we're going to be focusing on very simple 2x2 or 2x3 designs for examples, but we can get as complex as possible as you want, honestly. So you could potentially have a mixed design with 5 independent variables, and if only one of them is between subjects or only one of them is within subjects, it is a mixed design. A mixed design includes all the assumptions of both types of ANOVAs. So you have all the assumptions and statistical tests that you need to do for both the between subjects and within subjects designs. And it involves all nature of effects and size of effects issues of both types. So for example, a brief example here, we have males always the same at time 1, 2, and 3. So the n of 14 at time 1, the n of 14 at time 2, and the n of 14 at time 3 are all males and are all the same individuals. However, we also are looking at females across time 1, 2, and 3. So again, here that n of 12 is the same women in time 1, time 2, and time 3, but it is not the same people as in the males category. So we have a mixed design. We have a between subjects independent variable, males versus females, and a within subjects independent variable, time 1, 2, and 3. So why do we use a mixed design? Well, the first one, of course, is to explore individual differences in a within subjects variable. We're looking at the individual differences. It's basically referred to often as a split plot design. So in this case, we are basically looking for the same hypothesis we would in any of the other factorial designs. We're looking for main effects and interactions. But there are some other situations where we might use a mixed design. We can use it to control for potential confounds in a pure within subject design. In other words, we may actually want to look to see, is there a difference between participants that are in 2 different locations or 2 different genders, or potentially order effects. So for example, we might have a blocking variable or control variable that is looking at what order were people given the various predictions. So if we look at the audio lecture earlier today, or earlier in this week's set, so audio lecture 1, I used an example where people were shown 4 videos. A male introvert, a male extrovert, a female introvert, and a female extrovert. Does the order effects matter? Well, I could potentially set up a design where I actually have a between subjects variable that is order effects. So some people may have got the extroverts first and then the introverts. Some people may have got the introverts first, then the extroverts. And likewise, some people may have gotten male videos first, then female, female, then male. I could use those orders to create a categorical independent variable that is between subjects. Whatever order you got them in is different from the order other people got them in. Now, I don't have a hypothesis or a set of main effects based on order effects. I'm basically wanting to adjust for them. I want to see, did it matter? And if it did, I want to adjust for that. So if we're looking at individual differences to test to see if the effects of within subjects independent variable is different for conditions of between subjects, basically that's kind of a traditional 2 main effects and interaction design, just looking at 2 different types of variables. So for example, in this case, we have ratings of attractiveness, men versus women, a between subjects design, and then facial width that's been adjusted by a computer from narrow, moderate, and wide. So every participant is going to see men with a narrow, moderate, and wide face, and different participants will see the women with a narrow, moderate, or wide face, and then we get their ratings. Now in this case, we're actually interested in gender differences, we're interested in facial width differences, and we're interested in the potential interaction. So we have a mixed design where we have interesting hypotheses across the board. A split plot design, the within subjects IV tests for the effects of manipulation at this point, and the between subjects controls for the effect of time. So for example, our control in this case is no treatment, only time, while the experimental condition is treatment plus time. So in this case, we do have a split plot design. Everyone takes the pre-test and post-test. However, some people are given an experimental condition and some are not. This would be an example of a mixed design again. And in this case, we actually aren't that interested in the main effect of time. We're not necessarily interested in the main effect of treatment versus control. What we're really interested in is the only difference in the experimental post condition. And if we found that, that would tell us time didn't matter. What mattered was whether or not they got the experimental condition, and the experimental condition improved their DV, in this case, happiness. So in this case, we're not interested necessarily in any main effect, and in fact, we're interested in interaction, but only a very specific interaction. We want post-experimental to be the only significant difference in this cluster. And if so, we have a strong argument for an actual effect. So again, we're now using this design as kind of a way to put a covariate in or to adjust for the effects of pre-test versus post-test by itself versus in an experimental condition. So when we're interpreting a mixed design, the within subject's main effect of time is not interesting. The between subjects' main effect is not interesting because it's combining both pre-test and post-test scores. What is interesting is the interaction because it can indicate a differential improvement based on treatment alone. So again, we're not interested in the marginal means of time. We're not interested in the marginal means of experimental versus control. We're specifically interested in that final category of experimental post. If that is the one significant improvement, we have a strong argument that we actually found the impact of an experimental condition or a treatment on our DV, happiness. We can also do a blocking design, and I was referring to this earlier, where we evaluate the effects of within subjects IVs across blocks of potentially compounding variables. So we basically can rotate the order of presentation. This is often also referred to as doing a Latin square. And the idea behind a Latin square is that you create a number of categories of presentation orders where each independent variable's factor, the within subjects variable, appears in the position once. So an example, if we had a within subjects design where you are rating three candidates, Romney, Santorum, and Gingrich, and at which point you're going to rate all three on an outcome of how conservative you think they are. However, you're worried that maybe if you rate Romney first, you'll use him as the base for how conservative the other two are, and likewise if you rated Santorum first. Therefore, we're going to do a Latin square. Some participants get Romney, Santorum, and Gingrich, Romney in the first position. Some get Santorum, Gingrich, Romney in the last condition, and some get Gingrich, Romney, and Santorum, Romney's now in the middle condition. And notice that Gingrich appears once in each position, and Santorum appears once in each position. This is the idea behind a Latin square design. It basically is adjusting order effects, but once we've done that, we also want to treat that as a potential independent variable to make sure it actually works. So in this case, what we're hoping to find is that there are differences in the ratings of the ratings. However, those differences do not change based on the order. So the mean of RSG versus the mean of SGR versus the mean of GRS should be the same, and in this case they are. So again, our within subjects main effect is what we're interested in. We're actually only interested in the main effect of the ratings of Romney, Santorum, and Gingrich. The interaction is only interesting if it actually indicates that there is a difference in our order. And again, our between subjects main effect is not interesting. It's simply a blocking variable. It's not theory driven. So again, I just kind of want to open you up to the reasons that we might use a mixed design above and beyond just the fact that we actually have the traditional main effects and interaction hypotheses with differing ways that we gather the data between and within. So again, just remember that our ANOVA assumptions, our between subjects ANOVA assumptions are that we have categorical IVs, we have a continuous DV, a single one, that there's independence between the scores, that they're normally distributed, and we have homogeneity of variance. And we need to make sure that this is true for any between subjects variables in a mixed model. Our repeated subjects assumptions, again, categorical IVs, a single continuous DV, sporicity, which we do need to test, and we need to test that for any repeated subjects variables in our design. Again, normal distribution, and once again, homogeneity of variance. But notice we don't have that independence because we expect them to be dependent on each other. So again, we need to check all of these assumptions. Some additional issues to remember. Issues of sphericity exist for all effects that involve a repeated measure where the number of conditions is greater than 2. So again, if we have a variable with only 2 levels, we're fine. It's when it's greater than 2. And we test that with Malachi's test. Then the homogeneity of difference variance, if we find a difference in a repeated measures, again, there's some adjustments. We could, if sphericity is not assumed, we could use the Hung-Felt, the Greenhouse Geyser, the lower bound, or we can actually do a multivariate test instead of the test that we're using. And again, we do need that homogeneity of variance, Levene's test, for all these variables as well. We're not going to go much into the Hung-Felt, the Greenhouse Geyser, and the lower bound. Simply know that if you actually have violated the assumptions of either sphericity or homogeneity of variance with a repeated measures design, it's time to get that textbook out and do a little bit of research of, based on the reason that you found that problem, which one of these adjustments is probably the one that you should be using. Again, partial eta squared is going to be our effect size for both of these variables, whether they're between or within, and the nature of the effect options differ based on the type of IV. Between subjects, we're going to have to do post hoc tests and planned comparisons. Within subjects tests, we can't do post hoc tests, but we can do planned comparisons. And interactions, we can again look for simple main effects and simple interaction effects. Our partial eta squared again is going to be 0.01 is small, 0.09 is moderate, and 0.25 is large. And just as a quick reminder, we still need to test the actual dependent variable to make sure that it is normal. We need to look for skewness and kurtosis across that DV regardless of what else we're doing in a mixed model design. So just remember that as we continue to get to more and more advanced statistics, it's not giving us license to ignore the descriptive tests that we need to do before running any analysis. ANOVA, both repeated and within, have an assumption of normality, and we need to test for that normality. We need to check each one of our DVs or columns that have a DV in it to make sure that they're normally distributed.